Hello and welcome to Dr. D's Math. In this video I'm going to give an introduction to trigonometry by relying on some prior knowledge from geometry. Trigonometry is the study of triangles, and we're particularly interested with these three ratios or functions: sine, cosine, and tangent, and those all relate to this unit circle. We have a circle with a radius of 1. If our r equals 1, then we should recall that the circumference is 2 pi r, so in this case it's 2 pi times 1. And so one revolution around this unit circle is going to be 2 pi units. And those units can be called radians. And so when you see 2 pi or these circle angle measures in terms of pi, then we're working in radians. So at the start, we're always going to start in the x direction, in the positive x direction, along the x-axis there in the first quadrant, and the angle is going to go up, revolving around the unit circle in a counterclockwise direction. We're going to call that angle theta. Theta can be measured in degrees or in radians. And so just working around the circle, we're going to start with 0. Our milestone measures are 30 degrees or pi over 6 radians, and then 45 degrees or pi over 4 radians, and then the next one 60 degrees. And these are important because of triangles. These are kind of like milestone parts of the unit circle because of 30, 60, 90 triangles and 45, 45 right triangles. So that's 60 degrees. And then the next one, pi over 2, is 90 degrees. Then 30 degrees past pi over 2 is 120 degrees, or 2 pi over 3. 2 pi divided by 3, 120 degrees. And then 45 degrees from 90 is 135 degrees, or 3 pi over 4. And then another 30 degrees. We're halfway between 120 and 180, so that's going to be 150 degrees, or 5 pi over 6. And then we've got pi, or 180 degrees. And I think if you want to figure out the big numbers, 3 pi over 2, 3 pi over 2, or 270 degrees. And then 2 pi is 360. And that's the resting position for that angle. It'll restart the cycle again. Going back to more angle measures, 210 degrees is the next 30. And then that's going to be 7 pi over 6. Next is the 45 degree marker, which is 5 pi over 4. 5 pi over 4 is 180 plus 45, which is 225 degrees. And then the next 30 degree measure is 270 minus 30, which is 240 degrees. Then it's 7 pi over 6 plus pi over 6, so it's 8 pi over 6, or simplified to 4 pi over 3. And then 30 degrees from 270 is 300 degrees. 4 pi over 3 plus pi over 6 is 8 pi over 6. Plus 1 pi over 6 is 9 pi over 6, gives us 10 pi over 6. We're going 1, 2 measures here, 30 and 30. So that's going to be 5 pi over 6, or 10 pi. 10 pi over 6, or 5 pi over 3. And then we've got another 45 marker, 270 plus 270 plus 45 is 315. 315 degrees, and 7 pi over 4. And the last one on our long revolution around the unit circle, 11 pi over 6, and this is 360 minus 30 degrees, or 330 degrees. And so you might notice that here we're working in sixths, pi over 6, whereas up here we're working in pi over 3. For simplification, if you're trying to memorize these angle measures in terms of radians, that might help. And so when working from degrees to radians, if 2 pi units or 2 pi radians is one full revolution, that means that's going to equal 360 degrees. When we look then at our famous triangles, 45, 45 right, or isosceles right triangle, then we know that we have sides x, x, and x root 2. And so we can, well, I just got ahead of myself a little bit, I suppose. Let's think about the degrees, and let's take a step back from that one. Sorry about that. Got a little off track. Think about our 45 degrees. 45 degrees, we want to know how many radians it is. We don't remember that it's that spot there on the unit circle wheel. And so we know that it's some fraction of 360 degrees. We can remember there are 360 degrees in one full rotation of the circle. And so we also know that there are 2 pi radians. That leaves us with an opportunity to cross multiply and divide, or the butterfly method, as some people might have learned it. So we got theta times 360. 360 theta is equal to 45 times 2 pi. 45 times 2 pi. And then we can just simplify. We're going to get theta is equal to 90 pi over 360. So theta is equal to 90 and 360 share a common factor, which is 90. And so that gives us pi over 4, and that checks out up on our wheel up there. Now moving back to that isosceles right triangle, say we've got a 45, 45 right triangle, or an isosceles right triangle. We know that these two sides are equal, and this one is x root 2. We can verify that through the Pythagorean theorem, x squared plus x squared equals 2x squared, and so we need to take the square root of those. Then this would be our hypotenuse side over here. The square root of 2x squared is going to be x root 2, so that checks out. The next step is to work backwards. So we know that if we can determine what these side lengths are, then we can find the hypotenuse. But what if we know the hypotenuse is 1, for example, in the unit circle, if this were the radius of the unit circle, and we were at, and if theta here were that 45 degrees, and we would be at that point on the unit circle, would be that peak there, that vertex of that triangle. And we only know the radius, but we also know that we have that angle, 45 degrees, so x and y are the same. This is going to be our x over here. This is going to be our y. So we know that we're 1 unit to that circle's edge there, but we don't know what we are on the x and the y, so we want to find an ordered pair there so we can calculate our trigonometric ratios. Well, if 1 is equal to x root 2, then we can just do some algebra. X is equal to 1 over root 2, and if we wanted to simplify or rationalize the denominator, that's root 2 over 2. And that's one of those special decimals, 0.707. The other's 0.866 is the other one. And that's going to be our x. That's also going to be our y, because x and y are equal in this case. And so root 2 over 2 is where we are on the x. And that's also going to be our cosine value. And so if we wanted to say what is the cosine of this theta here, that's adjacent over hypotenuse. In this case, it's the x over the 1, which is, as I just showed a moment ago, root 2 over 2. And then also sine opposite over hypotenuse, which is y over 1. In this case, it's also root 2 over 2. And then the tangent at 45 is going to be the opposite over the adjacent, which is the x over the y, or 1, because they're equal. And so that opposite and adjacent isn't irrelevant to this unit circle. In fact, that's how we get our ratios, by looking at those triangles inside the unit circle. So if we had all three of those triangles all together, we've got our 30, 60, 90 this way for 60 degrees. And then we've also got, do it in a different color. We've also got our 45, 45 right. That's not quite the scale, but we'll call it good enough. And then we've also got our other 30, 60, 90 triangle down here. And in each of these cases, we have some ordered pairs for this point that lies out there on the unit circle. For this first one here, that point is going to be 1/2 on the x, and then root 3 over 2 on the y. For the second one, it'll be root 2 over 2 on the x and the y. We just saw that a moment ago. And for the third one, when we're at 30 degrees on the unit circle, that point's location is root 3 over 2 and 1/2 on the y. And you can see that the 60 and the 30 are just swapped. These two here are just mirror images of one another. And if we wanted to confirm that just a little bit more clearly, more concretely, let's take that 30-degree angle. That's again not to scale. And we're supposed to be at root 3 over 2 and 1/2. Well, if we're at 30 degrees here, then we know that this hypotenuse is equal to the shorter leg times 2, 1/2 times 2, which equals 1. And then this longer leg is supposed to be 1/2 times root 3. So indeed that checks out. And we already did the 45, 45 right. The other thing that's really important in trigonometry that will lead into calculus and higher order studies is the function sine, cosine, and tangent. And that's really just as the angle theta moves counterclockwise around the unit circle, what shape does that ratio take? And for sine, it looks like we start at 0 because on the x-axis we have 1 on the x-axis and 0 on the y for sine, which is the opposite over hypotenuse, or the y over 1. If there's 0 on the y on that unit circle, as we're just starting, then there won't be anything in this ratio. And it gets up to pi over 2, 3 pi over 2. It gets up to 1 at pi over 2, and then back down to 0 at pi, then down to -1 at 3 pi over 2 and back up to 0 at 2 pi. And we can see that this shape for the period of 2 pi, we can see that this shape is modeled in that ratio of opposites to hypotenuse, or the y value. As we start on the x-axis and move counterclockwise up to pi over 2 for the sine function. Now at pi over 2, our y location is 1 and our x is 0. If y is 1, then at pi over 2, we should have a peak. Then back down to 0 when y is 0. Again on the x-axis at pi, down to -1. Y is at -1 over here. And then back up to the start for that sine function. Now if we have a look at the cosine function, they're basically the same thing. It's just that instead of starting at right there at 0, the cosine function starts up here, and then it's going to end a little bit further. I'll show you what I'm talking about. Going from -1 to 1, same period, 2 pi, and we're going to split it up the same, pi over 2, 3 pi over 2. But instead of starting at 1, it's starting at, instead of starting at 0, it's starting at 1 and then crashing to 0 at 2 pi, and then going down to -1 at pi, and up to 0 at 3 pi over 2, and ending back up at 1. Because recall that the cosine is the adjacent over hypotenuse, which in this case is the x divided by 1. So if we're starting at 0 on the x-axis and moving counterclockwise, the x when we're at 0 is up at 1, and then we're moving counterclockwise to pi over 2 or 90 degrees. Where there is no x, we're right there on the y-axis, and then continuing along until we're at 1 on the x, -1 now. And then again back around to 0 when we're on the y-axis, and finally resting out at 1 full revolution. And finally, the tangent function is going to be a little different, because tangent theta equals opposite over the adjacent, which is the y over the x. So every time that x is 0, that means on the y-axis there at pi over 2, -pi over 2, or 3 pi over 2, then we're going to have something undefined. So in fact, the tangent period starts at -pi over 2, if you want to see the 1 full revolution, so to speak. We'll start at -pi over 2, and then it'll end at pi over 2. And it's going to go from -infinity to positive infinity. We've got some asymptotes here at -pi over 2 and pi over 2. And the function itself takes a pretty flat approach around the origin there, but then heads up towards infinity pretty rapidly after that. And that follows because at pi over 4, we should actually be at 1 at pi over 4. So that my graph is a little off here. Should be at 1 at pi over 4, and then it heads up really quickly after that. And then we should be at -1 again, because at 45 degrees are... So that's not really doing it justice. There is a pretty strong curve in here. It is more or less like a cubic function. With milestones, again, the only thing we can really say is that they're equal there. X and Y are equal at pi/4. And then we've got an asymptote at positive and -90, as reflected here on the graph. All right, welcome. This has been Dr. T's Math. Thanks for listening.